We shall look at a few problems associated with Newton's second law here. Problem 1. A block is projected up a frictionless inclined plane with an initial speed of 3 meters per second as shown. So what you have is a block that is projected up this inclined plane with an inclination angle of 30 degrees. So it has an initial speed of 3 meters per second, and it's going to go up and go against gravity. So the gravity will tend to slow it down, and it will move up to a certain height, and then it will stop. Now we want to know how far up the plane does the block go, and how long does it take to get there. And finally, what's going to happen to this block? It's going to come down back to the original position and find the speed when it gets back to the bottom of the plane, the original position that is. Let's take that plane to be the direction of positive x-axis. So that is the direction along which the motion occurs. Let's assume the block gets to this position before stopping, and it is at a distance of, let's say, d along the plane. Of course, we have a set of dynamical variables, the initial speed, which is 3 meters per second, and then at the point where it stops, the final speed is quite simply 0. Now we want to determine that distance, but we need to know the acceleration. So what is the acceleration or deceleration of this block? To find that, let's look at the free body diagram of this block. Now let's say this is the block as it moves up to the final position. Now we know the angle of inclination is 30 degrees. Let's call it theta for now. Let us list all the forces that are acting on this block. The first is the weight of the block, mass times the acceleration of gravity. The second is the normal force from the plane onto the block. Let's call it m. Now this weight has two components. One component is acting perpendicular to the plane, and the other component is acting parallel to the plane, W parallel. It is this component that is slowing the block down. So let's figure out what that component is. This is the hypotenuse, W. This is one side of the triangle, W parallel, and this is W perpendicular. The angle between W and W perpendicular can be figured out from this diagram right here. That is this angle. If this is theta, this is 90 degrees, so this must be 90 minus theta, so this has got to be theta. So this angle here is theta. So this is 90 degrees, so that must be 90 minus theta. What that means is the component of weight parallel to the plane is quite simply W cosine of 90 minus theta, or sine theta. Now we are ready to calculate this acceleration. So W parallel is the one that's responsible for the acceleration down the plane. And now we can figure out what that A is. So A is the net force along the plane, which in this case it's just W parallel because there is no other force in that direction, over the mass of the block. So the net force is W parallel over mass. W parallel is mg sine theta over m. M cancels, and you get g sine theta for the acceleration. So there we go. The acceleration is g sine 30 degrees for this problem. Now we can use kinematics to answer part A. So from one of the equations of kinematics, which says the final speed squared minus the initial speed squared equals 2 times acceleration, the distance traveled. We know the final speed is 0. The initial speed is 3, so square that, equals 2. Now the acceleration, the magnitude of the acceleration is g sine theta, but now look that it's acting in a direction opposite to the positive x-axis. So it's going to be minus g sine 30 degrees times x. And you can determine x. In this case, it is quite simply d, which will give you 0.917 meters. And that's part A. Now part B, how long does it take to get there? We can use another equation of kinematics to solve for the time, that equation. So the final speed is 0, the initial speed is 3. Acceleration is minus g sine 30 degrees, and let's call the time capital T. And you can solve for capital T. And it's going to be 0.612 seconds. Now let's look at part C. For part C, what happens is that it's going to come back down. So now the highest position would serve to be the initial position. So the initial speed is 0 now. The final speed is something which we want to determine, the same distance it will travel through. And now it is speeding because it's now going down the plane with an acceleration g sine 30 degrees. We can use the same kinematics equation to solve for part C. V squared minus u squared equals to a d, where now v is what you want to determine. U is now 0, that's u, equals to, the acceleration now will be positive because the object is accelerating down the plane, causing the speed to increase with the same magnitude, g sine 30 degrees, times the distance d, the same distance 0.917. Now we can solve for v. So when you solve for v, you get 3 meters per second, the same speed with which it takes off. And this is to be expected because we are dealing with a frictionless plane. Problem 2. A 35 kg boy and a 7 kg box are on a horizontal frictionless surface. So this surface here is frictionless. The initial distance between them is 12 meters. They are connected by a rope. So that is the rope. And it has negligible mass. Now the boy exerts a horizontal force of 6 newtons on the rope. The boy is pulling the rope that is connected to the box. Find the acceleration of the box and the boy, and also how far from the boy's initial position do they meet. So what's happening as this boy exerts a force on the rope, the box will move to the left, and at the same time the boy will drift to the right because we are dealing with a frictionless surface, and they will move with different acceleration. Let's call it a boy and a box. And at some point they will meet at some distance, say here, and we want to determine what that distance is. So let's first determine their individual accelerations. The best way to do this is to sketch free body diagram for the boy and the box. So let's start with the boy. So you have this boy on a surface. So what are the forces acting on this boy? So the first is, of course, the weight of that boy. And then you have this normal force. And the other force is the force exerted rightward from the box. And that force has got to be the same as the force that the boy exerts on the rope. And that is 6 newtons. So that means there must be an acceleration that way. Let's call it A sub B. And we can determine from Newton's second law that states the net force on boy equals the mass of the boy times the acceleration of that boy. Now the net force along the horizontal direction is 6 newtons, so that is 6. The mass of the boy is 35 kg, that's given right there. And the acceleration of the boy can be determined. And you will get 0.17 meter per second squared for the acceleration of the boy. Now let's look at the free body diagram for the box, like that. So what are the forces acting on this box? The weight of the box, the normal force on the box, and of course the force in the rope that is attached to the box, and we know it is 6 newtons. So the acceleration of the box is also along that direction. So in this case, F equals to the net force on the box is the mass of the box times the acceleration of the box. So the net force on the box is again 6 newtons. The mass of the box is given to be 7 kg times the acceleration of the box. And we can determine the acceleration of the box to be 0.86 meter per second squared. We note again the acceleration of the box is leftward, so that is ABX, and the acceleration of the boy is rightward, AB. So how far from the boy's initial position do they meet? For that, let's assume that the surface is the x-axis and the initial position of the boy is x equals to 0 mark. The boy is moving from rest and it's moving rightward with this acceleration. So the acceleration is constant. So that means the kinematics equations will be half AB, which is 0.17 t squared. Since the initial speed of the boy is 0, there is no ut term, and it's starting from x equals to 0, then the initial x-coordinate is also 0. So this is the equation that describes the change in x-coordinate of the boy. Now let's write down the equation of kinematics for the box. So the coordinate of this box would be half. Note the acceleration is leftward, so you have to add negative there, minus 0.86 t squared. It also starts from rest, so the original or the initial speed of the box is 0. There is no ubx t term, but the initial coordinate of that box is x equals to 12, so let's not forget to add that. Basically, this is that kinematics equation that look like this, a half at squared plus ut plus x naught. So we have applied this equation to the box and also to the boy. When they meet, the two coordinates must be the same. So let's determine the time at which that happens. Let's call it capital T. So by equating half 0.17 t squared to xbx evaluated at t equals to capital T, we get this equation, which enables us to find the time at which they meet, and we're gonna get 5.14 seconds. Now substituting this expression in here, we will be able to find the x-coordinate of that boy at that time. So assuming, let's say, their positions coincide there at, let's say, xp. So xp occurs at t equals to capital T. It's going to be half 0.17 5.14 squared. So I've taken capital T for the value of time in this equation, and you're going to get 2.24 meters, and that is the answer for the last part. So that means they will meet at a distance of 2.24 meters from the boy's initial position, which was x equals to 0. Thanks for watching.